Hi, in this video, we're going to discuss about the short channel effects that is one of the most significant factors in modern semiconductors. As you see, there are some kinds of capacitances in MOSFET structures. As you can see, in the first row of photos, if we plug the drain and source and the body to lower voltage and high voltage on the gate, we can see the oxide capacitance and some other factors of capacitances. With that said, if we put around 0 voltage and from negative voltage between before and flat band voltage, that is when this means the channel is not accumulated with the major carriers and not turned on enough that the channel has been opened. With this, there is a depletion region inside the body and the oxide capacitance in series. Because the series capacitance with the series capacitance, the total capacitance is lower than the oxide capacitance itself. So in this region, the capacitance itself is lower, is kind of lower. However, if we put negative voltage or positive voltage in the gate, when in case of this NFET, if we put positive voltage in the gate, the channel is going to be open and the capacitance rather than the oxide capacitance cannot be seen from body and gate because the current can flow through gate and into the channel and directly flow through the lower voltage. Because it is only one capacitor is seen, this oxide capacitance, if the higher voltage is applied, the capacitance we can see is higher than here. On the other hand, if we put lower voltage in the gate region, the accumulation of Hall also makes path from this channel to body. So the current, so we can only see this oxide capacitance. So the capacitance is also high, like as in the here. So the full amount of capacitance is like this. The is kind of low at the plus minus 0 and not turned on region, and the measure capacitance is high in the turned on MOSFETs and the accumulation region. If we put the circuit in these two things, that is, if we only plug to the gate and drain or the source, because the MOSFET itself is symmetric, if we put the higher voltage, the channel, because the channel is open and the current flow is like this, the capacitance looks like this. However, there's no current between these channel to the body when the lower voltage is applied. The capacitance can be only measured in this oxide capacitance. However, if we put negative voltage in the gate in this picture, there is no current flow through because we didn't apply this from this, but with this junction capacitance with the, if we see here, there is a little bit overlapping from gate and drain with the, in the series capacitance, the amount of capacitance is low like this. So this is the gate and collector capacitance graph. Unlike this figure, if you can see, if we only plug the gate and the body in the, well, in the, if we put lower or like 0 and plus minus whatever voltage from gate and body, we can see this low end capacitance here. However, if we put high voltage of between gate and body, we can see a parallel capacitance, those a series capacitance in the body and the oxide. So the amount of capacitance is lowered in the higher voltage. This means if we measure capacitance from gate and body, we can see this graph. And if we put gate and drain or source, we can see this capacitance graph and the amount of the overall capacitance, we can see this capacitance graph like this. This is how, as you can see in the Google, if we search about the amount of the capacitance of MOSFETs, we can see this capacitance graph. Let's move on to the subthreshold swing. If we see this graph here, the amount of drain current is scaled in log scale, and before then the threshold voltage, we can see these. We sometimes call this slope as the subthreshold swing. This means if the gate is not turned on, this tells how much these transistors can control the voltage when, to be honest, how much it can cut the current. The amount of this swing, this slope is like this. Some kinds of logarithms. With that said, if we put some constants, we can tell it's about, in theory, it's around 16 millivolts per decade in theory. However, in modern devices, of course, I am going to tell about this later. The modern devices have the much poor subthreshold swing like this. That is, we are going to improve the devices to control the subthreshold swing better. Looks like this. It looks like this thief to turn off the current better. As you can see, for modern devices, because the channel length is relatively shorter than in the conventional devices, there can be a lot. If there is a lot of difficulties in controlling the MOSFET than in the older devices. We can call these effects in like short channel effects. One of the most significant short channel effect is punch-through effect. That is, if we look at the source and drain, there is always this depletion region around the source and drain components because the doping of source and drain is much heavier than in the body. So the depletion region is much larger than in the body. If we shorten the channel length relatively shorter than any boundaries, if we put the plus and minus here, the depletion region of drain is larger than than the zero voltage is implanted. With this short enough devices, the depletion region in the gate, in the drain and source can be overlapped, that the current can be flow through the depletion region. This is called the punch-through effect. This means even if we don't if we don't give the gate any plus voltage, the the leakage current can flow easily than in the older long channel devices. Let's look about this punch through in detail. With this uh, depletion region, we can draw the energy band diagram like this. In the depletion region, the band is, because there is no because the hole is depleted in the depletion region, there are much more electrons than in the body because the holes are depleted, and the amount of electrons is more than in the body. This means the virtual channel, well, even we don't apply the plus voltage in the gate, the possibility of leaking of current is higher than in the body. With this, if we with this said, the punch-through effect makes the sub-threshold swing much worse than in the long enough channel devices. One way to deal with this punch-through effect is to dope the body substrate harder than in the another than the than in the normal devices. This means the amount of the depletion region depends on the amount of the doping elements, the amount of the doping elements. If we put the doping material more than in the normal materials, the depletion region is gets shallower. However, the increased doping causes the poorer mobility because the chance of scattering is higher than in the normal devices. So this method is not widely used until now. Another way to deal with the punch-through effect is the silicon on oxide. This means the body is caught with is caught by the insulator, so the area where between the drain and source is fully depleted, or well, even if the body is not small enough to fully depleted, but as you can see in the diagram, the depletion region cannot be larger when plus and minus the signal is input. So the punch-through effect is much less than in the normal devices. However, the fabrication of silicon on insulator devices is much more harder than the normal devices. So it is much harder to make, and it's much more expensive than the normal devices. Moreover, because the insulator is also insulative in heat, so the heat cannot dissipate that much. This means the heat is trapped in this narrow area, so it's more likely to be degenerate in degenerate faster than in the normal devices. We, however, if we put another material in the body, it then looks like with the another band offset like the heterojunction diodes. If we put the narrower band gap in this channel and wider band gap in this body, the amount of the amount of the width, uh, the amount of difference in width is the band offset. So the depletion region cannot be large because there is a electron wall here. Well, this at least is much easier than making silicon insulator devices, but let's look about this later. Another thing we need to discuss about is the threshold voltage role of effects. If we put the drain voltage higher than 0 volt, the energy band graph looks like this. The energy level of drain is lowered, then low voltage is introduced. In the short channel devices, the effect of the lowering the effect of drain voltage is much impactful than in the long channel devices, so the threshold voltage even is lowered. This is called drain-induced barrier lowering effect, as called as DIBL. Another thing we need to discuss is the velocity saturation effect. This is when we put high voltage from between drain and source, the amount of flow of electrons is at some point cannot be higher than in the resistive area, triode area. This is because with the much force of voltage, the flow of electrons can scatter. With the much power we get, the scattering, and as long as the phonon scattering like this it gets higher and higher. With that said, the amount of current is now saturated at some point. In the long channel devices, the amount of the current saturation looks like in the second order function. However, if we put this velocity saturation formula in the current formula, the amount of saturation current in the short channel devices looks like in the first order function, because the saturation velocity, if we put the velocity saturation formula here, the order is reduced into first order. This means with the velocity saturation is introduced, to be honest, more likely in the more likely in the short channel devices, the amount of flow of saturated current is lower than in the longer channel devices, because the saturation of current or the degradation of velocities are introduced because of the electrons in lattice. The lattice electric field is second order integral of the amount of doping concentration. To deal with this, we put the lightly doped area in the overlapping of gate and drain and the gate and source. With this, the amount of electric field is much lower than in the in the conventional devices, the electric scattering and the saturation of velocity is better than in the in the older devices. On another way to deal with the point-through effect is putting halo junction or some area be heavily doped and as same in a same doping kind in the body in just below than the drain and source. This is because the depletion region is blocked in the halo junction, so the depletion region is less likely to overlap. Let me look about the gate rather than drain and source. If we put the negative voltage in gate and the zero voltage in the drain or source, in this N plus region, because the voltage is minus voltage is applied to the gate, the energy there is the region of the depletion region is wider than in the normal situation. This means if we as we see and if the with this energy band diagram, the the width of band gap is lower than in the normal state. The, this means the holes in the substrate can be warped or tunneled into drain or source. This is called the gate-induced drain leakage, or as called as GIDO. With this effect, if we put the negative voltage in the gate, the amount of current flow is not zero, but a little bit of the current leakage flows from drain to source. In modern devices, the GIDL effect is higher than in the conventional devices. So the IDVG graph looks like this. Another thing we need to consider is about the contact. As we can see, we put metal on the surface of drain and source. If we scale down the devices, the amount of contacts has to be narrowed down because we need to scale down all the device itself. If we don't scale down the contact and only the length of channel is scaled down, we cannot see the total scaling down effect on the devices. With this, the amount of resistances for other factors can be lowered, but because the amount of contact is also narrowed, the resistance for contact it cannot be that lowered by scaling down devices. With this, the resistance stays relatively high while the capacitance is lowered when we scale down devices. This means the time constant tau that is R by C or R with R times C, even if we scale down the capacitance, however the resistance stays high, the amount of time it needs to turn on and off stays relatively high. With everything considered, on the short channel effects, the scientists and the engineers have moved on the FinFET structure. That is, we make the gate part like this with this shape, the body substrate like this, and the gate to wrap around the body. That means we can control the flow from three directions. That is one of the biggest breakthrough in the semiconductor industries. So this FinFET structure is widely used until now. Thank you for listening.